Welcome to session 6 and our first in a series of 3 lectures on survival analysis. Start as usual with our learning objectives and outline. So at the end of today you should be able to define the main types of censoring and what censoring is, define the assumption of uninformative censoring, define the survival function and the related hazard function and cumulative event function, perform a Kaplan-Meier estimate and interpret it, perform, interpret, and identify the assumptions of the log-rank test, define and calculate potential follow-up time, and finally calculate median survival time. So you're going to learn lots today. And we'll start with the introduction to censored data and types of censored data and this assumption of uninformative censoring. We will talk then about the survival function and Kaplan-Meier estimator of it, and discuss how to compare groups using the log-rank test. And you have a couple of textbook resources. As usual, there is a chapter in your textbook Widdinghoff, but I have also provided a tutorial paper which I like quite a lot called Survival Analysis Part 1, Basic Concepts and First Analyses, which I think is in some ways simpler and more intuitive than the textbook on this topic. So let's start with an introduction to censored data. And perhaps rather than saying censored data, I should say time to event data. This is the more fundamental thing. And what I'm referring to is generally time to the occurrence of a particular event, such as death, disease recurrence, or any other experience of interest. And the key attribute of this type of data is that our outcome variable is time, such as the time from the beginning of an observation period, such as surgery, to an event, or to the end of the study or loss of contact or withdrawal from the study. This kind of data comes up with research questions such as, what is the median survival time in years of patients diagnosed with a certain disease? What is the probability of those patients surviving for at least 5 years? Or are certain personal, behavioral, or clinical characteristics correlated with a participant's chance of survival? And in the clinical trial context, is there a survival difference between two groups, such as the treatment group versus the control group, or a group exposed to having some exposure versus an unexposed group? These kind of data require some special techniques for a couple of reasons. One is that these times to event, are generally not normally distributed. They tend to be more commonly exponentially distributed. That is, you have a lot of events initially and then fewer events over time, typically, but it can take any number of different distributions. And the second reason is censoring, that it is common to observe individuals for differing lengths of time. And at the end of that time, it may end because there is an event, or it may end because that person moved away, could no longer be contacted, or the end of the study was reached. So censoring is a key challenge in this kind of analysis. And just to give you an idea of why, let's consider a study with just 4 patients, a hypothetical study, where patient 1 dies 1 month after diagnosis, patient 2 dies 12 years after diagnosis, and then patient 3 is lost to follow-up after 1 month, and patient 4 is still alive after 12 years of follow-up. So first question, which of these patients are censored? Well, these 2 are censored because these are the patients where we don't know whether they lived or whether they died. All we know is that patient 3 was still alive after 1 month and patient 4 was still alive after 12 years. Second question, how would you rank these patients in order of disease severity? Well, I think it's pretty clear that patient 1 had the worst outcome. They died 1 month after diagnosis, so that's a very severe disease. Now, patient 2 also died, but they died 12 years later, so that's clearly a less severe disease, and potentially they died of something else. So it's pretty clear what the ranking is here. But what about patient 3? Patient 3 is lost to follow-up after 1 month. It's really not clear how severe that patient's disease was. It's clear that it is less severe than patient 1 because after the same length of follow-up, patient 1 died and patient 3 did not. But compared to patient 2, we just can't say because we didn't follow patient 3 for 12 years. And then finally, patient 4, well, at least it does seem clear that patient 4, who is still alive after 12 years of follow-up, they have a less severe disease than patient 1, and they also have probably a less severe disease than patient 2 because they are still alive after 12 years of follow-up. But again, we can't really say in a comparison with patient 3 because we actually have very little information about patient 3. So if we're asking about the relationship between a treatment and exposure and risk of death, we have to have a way of accounting both for whether a patient was dead or alive during the course of the study and how much follow-up we had. Clearly, if we looked only at survival without paying attention to the follow-up, we would not have a complete picture of these 4 patients. So what I showed you on the previous slide was an example of right censoring, and you'll see in a figure I'll show you later why it's called right censoring. But this means that the event, if it occurred, happened past the end of the observation period. So if you're plotting time on a horizontal axis going from left time equals 0 to right to the greater time, it happened past the end of the right-hand side of that plot. That's right censoring. Left censoring means that we know that that the event happened, but we don't actually know when it began. So for example, a study investigating the time to occurrence of a cancer following the surgery that removed the primary tumor, if we examined that patient 3 months after surgery and saw there was recurrence, but we don't know where in that 3 months the recurrence occurred, then that's left censoring because we've observed an event, but we know it happened sometime to the left of there on that timeline. And then finally, interval censoring is one where individuals come in and out of observation. That is, it's censored both on the right and on the left, or we have different observations that can be censored on the right or on the left. And I took these definitions from a different source shown here. Another way that you may see censoring classified or uninformative censoring classified is by type 1 and type 2 censoring. And I'm just introducing, this isn't even in your textbook, but I just wanted to introduce them to you because you might hear them somewhere. Type 1 censoring is where the total duration of the study is fixed. So we start the study with a plan to continue for 2 years, or more generally, where that follow-up time might be different for different individuals, but it's still fixed for each individual. So the main point is that the time of the study, the time that we plan to follow up, is fixed. And then type 2 censoring is where our study cohort, our sample, is followed as long as necessary until a pre-specified number of events have occurred. And this is fairly common in clinical trials for drug efficacy and things where there's a power analysis done that determines that we will need a certain number of events in order to have sufficient power to detect a difference. So the disadvantage to this type of study is that the length of the study is unknown in advance. The advantage of it is that we know how many events there will be, and that is actually the thing that matters the most in power analysis of time to event studies. And then a third type of censoring, which is relatively common, is random censoring, where the censoring times for each individual in the study are random. They're independent random variables. So they occur at various times that are randomly determined. They're not preset by the duration of the study, and they're not set by how long we go for reaching a pre-specified number of events. All of these distinctions are not actually that important, most likely to you, because they're all analyzed in essentially the same way. They only they may make a bit of difference, at least the left, right, and interval censoring in how you set up the data, but the analyses are the same. So what is uninformative and informative censoring? This is important to an important distinction to make because all of our analysis depends on this assumption of uninformative censoring, and that is that the censoring of the observation does not provide any information about the survival or the time to event after that. The only thing it tells you is that the time to event exceeds the time of the censoring. Now, this assumption can be violated if, for example, a patient who is at higher risk of death causes them to drop out. That is, that someone who is at higher risk of the event, whether it be death or anything else, causes either them to stay in the study or to drop out. And this is similar to the assumption of data missing at random or missing completely at random. So it is okay if the censoring is related to other covariates predictors. That is, if males are more likely to drop out, but we have sex as a predictor in the study, that is okay. That would be data missing at random still. But for two patients who are the same except that their risk of an event is different, if that affects the probability of censoring, then it's a problem. Then it is informative censoring, and it is a source of bias that is very difficult to identify. So I'm going to introduce some functions that we're going to be estimating today, and that the rest of the survival analysis that you're going to learn depends on. So this first function is called the survival function, S of t, and it is intuitive. It is the probability of being event-free at time t. So if the event is death, then it's literally survival. If the event is something else, then it's just the probability of being event-free. So equivalently, it's the probability that the time that that an individual survives is at least t. It's greater than t. So I have an example data set with this lecture, this leukemia data set, which is a study of a drug called 6-MP. I'm not even going to try to pronounce this, but it's a maintenance therapy for children in remission from acute lymphoblastic leukemia, ALL. So there are 42 patients who achieved remission from the induction therapy, that is the initial therapy, and then were randomized in equal numbers to maintenance with 6-MP or a placebo. And then survival time was studied from the time of randomization until relapse. And these are the actual times from the data set. So in the placebo group, these are times in weeks. They vary from 1 to 11. And then in the treatment group, we see times. The first one is 6, and the last one is 35 with a plus. And this plus in the survival package in R is how a censored event is annotated. So this means that this person was alive at 35 weeks, and then it was censored, so there's no event. So their survival time was at least 35 weeks. So just looking at this data set, it looks like this is probably an effective drug, because we have all deaths in the placebo group. The longest anyone survived was 11 weeks, whereas in the treatment group we have survival up to at least 35 weeks, and no one died in less than 6 weeks. So I'm plotting here this treatment group, and I've simulated initiation times between 0 and 26 weeks, just to give an example of a typical study where the initialization and randomization time doesn't happen all at once. These patients are treated as they enter the clinic and start treatment. So that's not going to be all at the same time. But it's going to be from the start of the study here at 0 week to sometime later. And then I've plotted each of these with the time, and then I put a right arrow where it's censored, meaning that patient is still living at that time. And then the ones with an event, I've put an X here, meaning that patient has died, and it will not be alive beyond that point. So from the textbook, this is what is called a follow-up table for this study, and this is for the placebo patients here. And what it has is it has a row for each time point. It doesn't really matter whether it's 1, 2, 3, 4 weeks. What matters is just that it's a time point where either there was a censoring or an event. And it has written down here, there's one column for the number of people following. This is also called the risk set. And in other papers and discussions of survival analysis, you'll see this number of people followed called the risk set. This is the number of people who are at risk at each of these times. So we start out with 21 people in the placebo group, and then at this time, at week 1, there are the number who relapsed. There were none who were centered. And that's why the next week now we have 19 people being followed. And so what is calculated here, this conditional probability of remission, this is the probability of an event occurring in this week. And I'm sorry, apparently this is remission and not death. So, but since there were 2 events, it means that there's a 2 out of 21 probability of relapse and a 19 out of 21 probability of remission. So the survival function is 19 over 21, which is 0.91. So that function that I just told you on the last page, you can calculate it with a calculator. There's nothing fancy about it. It's 0.91 in this week. Now the second week, we only have 19 people left in the risk set. 2 of them relapsed. And so the conditional probability of remission in this week is 17 out of 19. So even though the same number of people relapsed, this probability of remission is a little bit lower because there are fewer people left in the risk set. And the total survival function is the probability of surviving to week 1 times the probability of surviving week 2, which gives us a 0.81. And if you continue this down, it's just the same thing every week, calculating this conditional probability of remission each week and multiplying it by the survival function of the previous week. And this is the Kaplan-Meier estimate of the survival function. So it's a very intuitive and appealing estimate. It's also just a basic probability function. It's based on the observed probability of surviving at each week. So even though I've just actually introduced it to you, I sort of snuck up the Kaplan-Meier estimate on you on the previous page by showing you how it was calculated. This is how you generally see it presented, and this is the most common plot that you will see in any study that performs a survival analysis. This is the Kaplan-Meier estimate of that survival function over time, and it's plotted here for these two groups. The 6-MP treatment group shown in salmon, that's the higher group, and the placebo group shown in blue, that is the lower survival group. So you can interpret this exactly as it says, as a survival probability as a function of time. And here you can see the observation we made earlier that the placebo group has very poor survival or very poor remission probability. This probability function goes down rapidly and is actually down to 0 at, I don't know, this is 23 weeks here. In the treatment group, we see it come down quite a bit more slowly, this probability, and at the end of the study, it's still 50%. So this is telling us that in this treatment group, by the end of the study, there is still a 50% probability of remission. And you'll see something else in here, these little marks. This is traditionally how a censoring event is shown in a Kaplan-Meier plot. So everywhere you see one of these little, it's actually a plus sign, means that there was a censored event there. Or sorry, there was a censoring there, an unobserved loss to follow-up. And everywhere where there's a drop, that is an actual event, because it means that at that time, because we observed an event, then there is a lower survival probability at this point. This plot down below you don't always see with Kaplan-Meier plots, but it's a very nice addition that I far prefer to see, and it makes interpreting this plot much richer and easier to do. And this tells you the number of people in that risk set. Remember, I said the terminology, the number of people at risk at each of these points. So this tells me that at the beginning, this is 21 people in each group. At 10 weeks, there are 15 people remaining in the treatment group and only 8 people remaining in the placebo group. And by the end of, or by 30 weeks, there are 4 people in the treatment group, 0 people remaining in the placebo group. So now that we have a survival function as a probability of survival as a function of time, it's fairly easy to define the median survival time or any other quantile. The median is just the time at which half of a group is expected to experience an event, such as death or remission. If there were no censoring, then this median survival time can be calculated in the obvious way. You just take all of your times to event and take the median. But with censoring, you need to use this Kaplan-Meier estimate because otherwise you're not accounting for the fact that some of those times end in censoring, whereas others end in event. This is straightforward to do. In R, the survival package has this function survfit. You define a new variable that is a survival object where you enter the time and the censoring variable. You'll get practice doing this. But you have one column that is the time, another one is whether the events are censored. It's 0 for censored event or for censoring, and 1 for events. And then here I'm using a model formula with just group on the right hand side, and it shows me this outcome from the Kaplan-Meier estimate that gives me an estimated median survival time. And I see that in the treatment group, the median expected survival time is 23 weeks, and in the placebo group, it is only 8 weeks. And then there's another calculation that's closely related that is called the median potential follow-up time. And this is a much less obvious entity, what this means. And what it is, it's the time for which half of a sample would have been expected to be followed in the absence of events. So if there were no events, how long would the median follow-up time be? And it's, again, not obvious. If there were no events, you could just take the median. Just like on the previous page, if there were no censoring, you could just take the median. And this is one I've actually seen done incorrectly in a number of published papers. It's useful when the follow-up time is not tightly controlled, such as a guaranteed certain amount of follow-up time, but is a random event, and you are actually unsure and you want to do a calculation to establish what the follow-up time was. And you can do this with what's called a reverse Kaplan-Meier estimate. And all you have to do then is reverse the censoring labels. So all of the censoring become events and all of the events become censoring. And I do that here just by going 1 minus the censoring variable. And then I see a median follow-up, median potential follow-up in the treatment group of 25 weeks. And I see an NA in the placebo group because there was no censoring in that group. They were all events, so it's impossible to estimate this. And even in the treatment group, it's here impossible to estimate a 95% upper confidence limit because there wasn't that much censoring. So we have no way to estimate the upper limit on how long people would have been followed up because there were too many events. And note here that the actual median follow-up time is half as long for the placebo group because because they ended in events, not in censoring. Okay, another related function is the cumulative event function, and all it is 1 minus the survival function. So whereas the survival function was the probability of surviving up until a certain time, this is the probability of having an event by that time. So if on the left here we're showing the survival probability, it always goes down. On the right is the event probability. It's just 1 minus the other one, and it goes up. Now the hazard functions are less intuitive and a little bit hard to visualize, but they are important because they're going to form the basis for proportional hazards analysis, which we will get into in the next session. So little h of t, the hazard function, is the risk of an event at any point in time. So it's like the microscopic risk of event at every point in time. So somewhere that the survival function is dropping quickly, that's a high hazard. If it's not dropping at all, that's a low hazard. And then this capital H is the cumulative hazard function, which is an integral of this little h. It's the cumulative hazard added up over time. This, I think, is not so important. It's the negative logarithm of the survival function, but not as easily interpreted. But it will be important, as I said, in the next class for Cox proportional hazards. All right, our last section is comparing groups using the log rank test. So we're not going to get into full regression analysis today, but you will have a tool for comparing two groups. And the log rank test, it's a workhorse, very important test in survival analysis that you can use to compare survival between two or more groups. The null hypothesis for it is that the survival functions for the population are equal at all follow-up times. So that S of t or any of those, the F of t, the H of t, they're identical for all of your groups at all times. And the alternative hypothesis is that those survival functions differ for at least one of the follow-up times, for at least part of the time. And this log rank test, it's very simple. It's just a chi-squared test comparing the expected versus observed number of events in each group overall in the study. So the observed is just the number, is just what we see, and the expected is based on this survival function. So I'm actually calculating this here with the survdiff function, and it's showing me here this number of observed events in each group, and it's estimating an expected number of events in each group based on the follow-up times. And then this bit is showing us into the guts of the chi-squared calculation, this difference between observed minus expected squared over expected. There's a chi-squared value calculated and a p-value associated of, in this case, 4 times 10 to the minus 5. So in this case, we would reject this null hypothesis of the survival functions being the same between these two groups. So that's good because it was quite obvious just from looking even at the raw data and also at the Kaplan-Meier plots that these were different. But this provides a p-value against the null hypothesis that those differences might have occurred only by chance, even with identical survival functions. And I'll just mention that there are other tests for comparing two or more groups like this, but this log rank test, in my observation anyways, is by far the most widely used, and I think should be the default unless you have a good reason for choosing another test. What I understand about these other tests is that they place more emphasis on late events or on early events, whereas all events are equally weighted in the log rank test. In the next session, when we get into proportional hazards models, you'll have additional tools at your disposal for doing hypothesis tests, especially in multivariate analysis. It's worth pointing out that the log rank test, you cannot use it for multivariate analysis. This is only for a single predictor of survival. So if you want to do something like adjusting for hypothesized confounders, then you actually need to fit a multivariate model, which we haven't gotten into yet today. Some notes about the log rank test. First of all, it's non-parametric, so it doesn't require any assumptions about the form of the survival curve. It does not work, and neither do Kaplan-Meier curves with continuous predictors. So I showed those nice two curves in the Kaplan-Meier plot because we had a binary predictor. We could have a categorical predictor with 3 levels and show 3 of those curves and still do a log rank test. But with a continuous predictor, we can't do any of those things. So we would either have to cut it and turn it into a categorical variable, or consider fitting a model such as we will do later. These tests do still assume non-informative censoring. Again, that is that censoring is unrelated to the likelihood of developing the event of interest, and that for each subject, their censoring time is statistically independent from their failure time. So to wrap up, censoring does require some special methods in order to make full use of the data, both the time to event and the presence of censoring, without just treating that as missing data. You've learned about the Kaplan-Meier estimate to provide a non-parametric estimate of the survival function that is just based on the observed probabilities of survival at each time in the study. And by non-parametric, I mean that we haven't assumed any form of the survival function. We're just estimating it based on the observed data empirically. And finally, the log-rank test provides a non-parametric hypothesis test under the null hypothesis of identical survival functions in each of the strata considered in that test. Thank you.